Okay, so we're back to talk about weak bases. Okay, now weak bases, similar kind of ICE grid situation, but remember this time hydroxide ions will be the product. Okay, so when we have a weak base, we're going to find through an equilibrium setting up the OH minus ion concentration. So when we work through the pH, we'll have to go through POH, which is the minus log of this thing, and then do a little kind of conversion at the end from pH, sorry, from POH to pH. Okay, so the classic example is of course ammonia. Okay, so ammonia is the weak base kind of poster child, so to speak. Okay, so we'll do a similar kind of work through like we did with the acids. We'll determine an equilibrium constant expression. Okay, so we have ammonia, which is a base, picks up a proton from water to make ammonium and hydroxide in solution. Okay, so we have, if I do a simple K expression, K equals products over reactants. Okay. Same deal as before. We can derive a new constant from combining a couple of constants here. So we'll just do that real quick. So K, oh, I've moved it out of shot, but let's bring it back, there we go. K times the constant, which is the concentration of water, equals a new constant, B for base, Kb, okay, which equals NH4 plus OH minus over NH3. There we go. Okay, if I'm more generic here, Kb for a generic equals conjugate acid times OH minus over B for base. We're using a more generic kind of form. Okay, so I always like to remember the ammonia example. I'm kind of a solid example kind of person. If you like a more generic kind of one, that's good too. Okay, so as we saw before, mineral acids were strong, mineral bases are also strong. Okay, so mineral bases or strong bases simply have OH as a straight passenger, right? So OH is in this salt essentially, which is a strong electrolyte pair. It completely dissociates. So whenever we see a kind of a metal with something, it's going to fall apart to make 100% ions in solution. So it's strong, it completely dissociates. Okay, so here we have another situation. This is also strong. You know, we can use KOH and NaOH interchangeably in lab. They do exactly the same thing. They give you a nice amount of hydroxide ions in solution. For every one KOH, I get one OH. For every one NaOH, I get one OH. Oh, typo. Kb. Kb, all products, now reactants at equilibrium. Equilibrium, speech marks, right? It's not really an equilibrium, it's a complete reaction. Okay, so then we have these, okay? We have, each of these has a recorded Kb, so they're all weak. These are all weak, okay? Because they have Kb values. A bit like if you have a Ka, they're all weak acids. Well, these are all weak bases. And we can do our, it's not, remember, a direct association for weak bases. It's actually reacting with water to make OH. So the weak base picks up a proton. Oh, to make hydroxide. That's a 4. Okay, we saw that one on the previous page. Okay. Similarly, maybe pause here and give those a go if you wish, but I'll just go straight with it. Pick up a proton. And finally, this is the one from your lab you're hopefully working on, right? Okay, so there we are. The bases pick up a proton from water to leave OH behind. Okay, now just like before, who's the king of the nerds, right? So who's the strongest of the week? Well, remember, it's all about value of Kb. The largest number here is actually the bottom number. Okay, 10 to the minus 4 is the largest value there. CO3 2 minus. This is why lots of natural sources of water are slightly alkaline. You go to the supermarket, you say, oh, alkaline water. It just has naturally dissolved calcium carbonate or chalk in it. Okay, so no biggie. All right, the weakest weak bases, look at the numbers, 10 to the minus 7, hydrogen sulfide ion. Fair enough. Okay. Recall products over reactants. A small number means less products, a large number means more products. Okay. Next page, we'll get on to some questions. So in a similar kind of way we did before, there are two kinds of questions, if you like, the forward question and the reverse question, just like it with the acids. But here, remember, we have OH as a product, okay? So when we do the minus log of that, we're going to get POH, and then pH plus POH equals 14, if you remember that relationship, okay? So we get this one, minus it from 14 to get pH, because we always quote pH rather than POH when we, when we do a question, right? So let's look at this. So find the OH minus concentration and pH for a 0.15 ammonia. Kb is known. Okay. So the plan, go to the ICE grid, solve for OH minus ion concentration, which is going to be X when we get to it. Okay. And hey, if we've got the OH minus concentration, well, you can find POH, and then hey, use the relationship here to find pH. Okay, so quite similar to the previous question, but the little twist on the end is always converting POH to pH. All right, so the execution. I'm kind of trying to be mindful to keep pulling this up so it doesn't go off the bottom of the page. I did see that. Okay, so NH3, H2O, NH4 plus OH minus. Okay. ICE. Did say at the top 0.15 moles per liter. The concentration of water is meaningless. It is a reactant, so we got to write it, but its concentration is meaningless for the math, if you remember. Okay, it's a constant. And then we have 0, 0. We don't know how much we lose, but there's 1 to 1 to 1 to 1. We lose X, we gain X. So 0, of course. Okay, then at equilibrium, what have we got? 0.15 minus X, X, and X. I know what you're saying. You're saying, when can I get out of the house? No, you're saying, can I do the same kind of approximation here? We did the weak acid approximation. Can we do a weak base approximation? Yep, we can. We can do the weak base approximation because Kb's are a similar magnitude to Kas. Therefore, Kb equals products, X times X, X squared over reactants, 0.15 minus X, small, X squared, approximately equal to X squared over 0.15. Therefore, I'll come down here. Therefore, X is the OH minus ion concentration, which equals X, which equals Kb. Let's put the number on it. Okay. So let me try and neaten this up a bit. Kb was 1.8. times 10 to the minus 5. Alright, that's KB. So x equals KB, 1.8 times 10 to the minus 5 times 0.15, like the very similar example, square root, which equals 1.6 times 10 to the minus 3. Running out of space a little bit. Okay. Therefore, POH equals minus log 1.6 times 10 to the minus 3, which equals 2.8. Therefore, pH equals 14 minus 2.8, which equals 11.2. Makes sense, right? The pH of a base is 11.2. Shocker, right? Okay. Group task. It's the reverse problem. Okay, it's the reverse problem. I want you to try that. Okay, normally if we did this in class, I'll have you work on it in little groups and then we go through it. The answer 0.0056 molar. Hopefully you get that. If you don't get that, ask a question in the comments area. KB, it's on the previous page, but KB for ammonia, 1.8 times 10 to the minus 5, you can use that. Okay, so that's the reverse problem. Feel free to confer with each other, ask me questions if you wish. Okay. Now, in the same way there's a relationship between KW and then PKW, H plus, OH minus, pH, POH, Ka and Kb also come into that relationship. Okay, and I want to show you the relationship between Ka and Kb. Well, just a simple little bit of algebra, right? So I've taken the classic ammonia example. Here's ammonium acting as an acid, okay? Here's ammonia, which we just saw, acting as a base, okay? So that's like the reverse reaction from above, right? So for that reaction, Ka equals products, H plus NH3 over NH4 plus. Fair enough. For the reverse reaction, this one, Ka in the reverse reaction, Kb in the forward direction, acts as a base in the forward, acid in the reverse. Products, NH4 plus, OH minus, NH3, okay, H2O. All right, now, if you remember, when we add reactions, we multiply K's, all right? So let's do that. So we're gonna add, and feel free to pause, give this a shot yourself. For speed, I won't write the state symbols, but you can do that. All right. What cancels? Well, NH4, NH3, H2O, and H plus, OH minus. Oh, interesting. Okay, so if you remember, KW equals H plus times OH minus, okay, which equals, add equations, multiply these guys, which equals Ka, Kb. If you actually multiplied these two together, you would find things cancelled. Okay, so if you want to bring that up and multiply it through, you get what would be left would be the same. Okay, all right. So equilibrium math can be applied. Okay, very, very simple idea. Let's write it down. Another equation to remember. Okay, Kw equals 1 times 10 to the minus 14, which equals H plus OH minus. That's what we've seen before. And it also equals Ka times Kb. If you like, it's the equilibrium constant for the forward reaction times the equilibrium from the constant from the reverse reaction equals Kw. Okay, because remember, this all happens in aqueous solution. This is all in the background, right? Okay, so, you know, some more reactions to remember. If I take the minus log of both sides, I get that. Okay, in much the same way as pH plus POH equals pKw, pKa plus pKb equals pKw, right? Where pKw is, of course, 14. Okay, so very similar. So a quick question. What is Ka for NH3? Well, Kb, as we saw in the previous question, 1.8 times 10 minus 5. Now if you think about it, Kw equals Ka Kb, therefore Ka equals Kw over Kb, 10 to the minus 14, 1.8 times 10 minus 5, one off the bottom, 5.6 times 10 to the minus 10. Okay. All right. Now, there is an old exam question. And yes, extra credit. Okay. So, just like the last one, we'll make this one also worth some extra credit. Okay, I'll talk you through it a little bit though. Okay, so here are the previous 2 extra credits. Hopefully you're working on these. I'm going to send me those pictures. Okay, so talk you through it. Codeine, weak organic base. Codeine has a pH of this, right? So the key word here is base, right? So work out Kb. You're going to do a grid. Okay. Calculate pKa. So once you've got Kb, you can turn it into Ka, just like we did, and then turn it into pKa. So there's kind of a, So there's a friendly roadmap, okay? So you've got Kb from the first part. Similar math to we just did at the previous page to find Ka, take the minus log in base 10. And everyone's happy, all right. That'd be plus 3 extra credit. Okay, so, you know, maybe you want to send it with your acid work. I'm recording this all on the same day, so let's try and make it a week from now. So the 7th. Okay, April 7th. Okay, so get this done by April 7th. Okay, some nice pictures to finish off. This is all in the appendix. We see full dissociation, partial dissociation, basically pictures from your textbook. That classic strength chart we used before. Another copy in here as well. So if you use that one on the last packet, you can use it here too. And some examples of common acids and bases. Okay, and you can just go through on some blank paper. Okay, that's the last one. All right, so we'll stop there. Again, any questions, discussion? See you next time.